Here actually we are talking about fixed point scaling, which means we want to keep a pivot point, okay, and according to this pivot point we will scale it. So for that there are 3 steps. We will translate it to the origin, we will bring the object to the origin, perform the operation, perform the scaling, and then translate it back. So it is our choice. We can go for 3 different translations, one after 3 different transformations, one after another, and then get the result, or we can use one composite transformation matrix for this purpose, multiply this single composite transformation matrix to our pixels and get the desired result. That's the thing. I believe let us see some other example where we need to combine your this thing, scaling with rotation as well. Okay. One example, if you want to perform rotation as well as scaling both, then let me show you an example where you will be able to combine those two. Suppose you want to do a particular scaling in a particular direction. Okay, this is your index, this was your object, and you want to grow it in a particular direction. Particular direction means you want to grow it in this direction. Okay. So what you need to do, you can keep it in this plane. Original was this plane, right, xy. Now if you will keep this in this plane and then you will increase the size, this may also help. Okay, let me try to make it easy for understanding. What actually we are trying to understand is, whatever it is in the original plane, if we rotate it a little and then increase the size and then rotate it back, our job is done, right? So what we can do is, suppose if certain situation occurs where you need to perform rotation, scaling and rotation again. So you are performing a rotation with theta, then you are performing a scaling with your sx, sy, whatever values, and then you are performing again a rotation. Okay, one will be some r theta, another will be reverse of it, right? Let me write r inverse of theta, means in a opposite direction. So what will happen? Ultimately what will happen, you will get a composite matrix after these 3 transformations, which may look something like S1 cos squared theta plus S2, this is Sx actually, this is y, Sy sin squared theta. I will have to delete this thing to write this thing, Anna. Let me write it here again. Sx cos square theta plus Sy sin square theta, then Sy minus Sx into cos theta sin theta and 0. Here what is there? Same thing, sy minus sx into cos theta sin theta, and here same thing, sx sin square theta plus s2, this is sy cos square theta. Okay. So this is an example of such transformation where you need to rotate it and then scale it, and then you can rotate it again. So similarly, you can have any kind of other composite transformation matrix where you may have any type of combination of these transformations. Here you are saying rotation, scaling and rotation. You may have rotation, scaling and translation, all three together, or any such things, right? So any such combination is possible and you can do. One thing that you have to understand, that whenever you multiply matrices, if it is A, B, C, three matrices are being multiplied. So you multiply A and B first, and whatever the result is there, you multiply it with C. It is same as you multiply A with the result of B and C. Okay, we call this property as associative property. This property is associative property. Okay, so no problem. One thing that you have to understand, that it is only associative, it is not commutative. What is commutative? Commutative means A dot B can be equal to B dot A. However, in our case, you should understand matrix multiplication is not commutative. That means A dot B is not equal to B dot A. Multiplication of A matrix with B is not same as B with A. Okay, I believe these are the simple things that you would be aware. Okay. So I believe now we can start talking about our other kind of transformations. Other transformations are basically reflection and shear. Okay, means it is shear actually. So let us start with the new thing.